Okay, welcome back to our computer vision class. So far, we start learning about using the deep learning in computer vision, and we learned about using the simple single layer deep neural network. And as we stated last time, there are two tasks that we can achieve with any model, any machine learning model in general. We can achieve two tasks. Task number one is classification. And for this case, I'm generating the probability that this object belongs to a specific class. So as we stated last time, we want to generate the probability that this image, the probability that this image belongs to the class of the cat or the car or the frog. So the output in this case is a PDF, a probability density function with the probability that this image belongs to this class, or the probability that I'm having this class of the cat given the image, which we call probability of y given x. So x is the input and y is the first class, then the second class, then the third class, all of them, y1, y2, y3, given the x, okay? This is the first category. And for this category, we learned two techniques we can use to calculate the parameter, because as we stated, now we're calculating f of xi and w. This is our neural network. So this neural network function of both xi and w. This xi is nothing but the input. W are the parameters inside my network that I'm tuning to produce this output. Okay? So my goal is to tune W. When we are saying tuning, means we want to change the value of W to achieve a minimum value of L. So L is a function that I'm trying to minimize. So I'm exploring all the space of W's to find this minimum L. And we are calling this L loss function. So for this loss function, we said that we have two common loss functions can be used for the classification task, which are the Hingst loss, or called support vector machine loss. The second one is cross entropy loss. The concept of the SVM loss or the Hingst loss is to separate the score generated from this classifier as much as we can between the correct and the wrong class. The concept of the cross entropy loss, if you recall, that we are trying to match the generated probability with the ground truth probability as much as we can, using the concept of entropy or KL divergence from the information theory. So here with the cross entropy, we are trying to match two probabilities. I have ground truth probability and I have probability generated by the model. Now I'm trying to match this with this, okay? So this is the concept of cross entropy loss. What about the second task? The second task, as we stated last time, called regression. May I ask the students who opened their computer, what are you doing? You are not taking notes, you are not watching anything related to the class. So why you are opening it? What is the meaning of regression? In this case, I'm not generating probability like in the classification problem. I'm generating score by itself to match an outer score. So I'm having X as an example is time, and Y is the price of stock or whatever it is. Okay? And my goal is to generate or design a model that can match the past and expect the future. Okay? In this case, the output here is a real value. It's not like the classification. For the classification, I'm having category, and for each category, I'm having probability value, which means it can be between 0 and 1. And the sum of all of them must be 1. For the regression, no. There is no limitation on the output. The output can be any value, positive or negative, depends on the technique or the value you are generating. For example, if you are generating a signal as an example, any signal can have a negative value with no restriction. If you are generating stock price, can the stock price be negative? The price, money. The money can't be negative. Okay? So it will be positive only. Okay? But it's real, it's continuous. There is no quantized level. No. It can be any value in between. Okay? Now, for this type of mission, what is the loss function that best match this task? The best one that we always use for the tasks of regression, some loss function called mean square error, which equal 1 over n summation over on n to the loss function between the required value minus the expected value. So this is ground truth, required value, and this is the expected or the generated value. If we take the difference between them, this difference can be positive or negative. Okay? In this case, the minimization process will be tough to achieve. That's why we are doing it with one of two ways. Technique number one is to take the absolute. If you take absolute in this case, if you have an error, it will still within the limit. So if it's small, the value here will be small. If it's big, the value will be big. That's not what I want. So it will look like V shape, something like this. Okay? I don't want that. I want it to be more convex, like this. How I can convert it to convex? We said simply square root. That's why it's called mean square error. So I'm calculating the error between the required ground truth and the expected one, then square it, then take the average or the mean over it. That's why it's called mean square error. Okay? So if the task is classification, those considered to be the best loss function to use. If the task is regression, in this case, the mean square error is the best loss function to use. Okay? Now, this function by itself can be considered in this form. Sum of all the values of all the samples I'm having. As we stated before, this is not canonical. It's not the best option to do. Why? Because in this case, I'm trying to consider the error between the required output and the generated value without taking into consideration the structure of W itself. Should it be bigger values or should it be small values? If you recall from last time, when we used the Henge loss, we said that if you have a specific value of W that make the loss function equal 0, double this value, it will make it also equal 0. Treble this value or fourth, it will make it also equal 0. So we don't have one solution, okay? I want to add constraints over W to make sure that I will not achieve bigger one. I want it to still small, and we'll see why in a second. For that purpose, they said I will add one extra term. We call it regularization term, R. This R is not function of X anymore. It's function of W only. So this R, function of W only. And all the purpose of this R is to minimize W. So I don't want to minimize the cost only, which is the error between the required and the given value. No, I want to minimize W themselves. And we call this regularization term. To make this regularization term balance between the loss function and the minimization of W, we added this lambda. This lambda is not automatically chosen for us, or not automatically selected for us. We have to select it. We are calling this lambda hyperparameter. Any parameter that we choose by ourselves to control or to adjust the algorithm is called hyperparameter. If the parameter, I'm selecting it through an optimization or automatically through an algorithm, it's called the regular parameter. Okay, so this is the difference between hyperparameter and the regular parameter. Hyperparameter selected by you, the developer. Regular parameter will be found through the optimization process. Now, as we stated, this lambda will make the balance between both of them. But what will happen if we have bigger W? How this will affect our data? Again, as we stated last time, those two W's will produce the same exact loss value. If you try for this X, try to use this W and this W and calculate the loss. In this case, this time this 1 plus 0 plus 0 plus 0. So the result here is 1. Between this and this, it will equal. It will equal 1 over 4, 1 over 4, 1 over 4, 1 over 4. The sum on the end equal 1. So this value equal this value. So from the loss perspective, they are equal. Okay? Now, which one should I choose? Theoretically and logically. This is using only one pixel. It ignores pixel 2, 3, and 4. I'm using this only and giving 0 weight to those. Does this make sense for you? So this means I'm using only this pixel to classify all this image. Doesn't make any sense, right? The other one, give fourth the weight for this, fourth for that, 1/4 for that, 1/4 for that. So it used the 4 pixels that I have in my image. That's why this one should be better. Now, assume that I defined the regularization term to be the summation of w's squared, which means all the w's I'm having here, I will square them and sum. In this case, the sum of all w's here will equal what? If you sum those, one over 16, 1 over 16, 1 over 16, 1 over 16, which is what? So the good W have lower regularization term. Okay? That's why we always try to add this regularization term next to the loss function or data loss function in the optimization process. Because the good W associated to lower regularization. So here I'm not optimizing one function, no, I'm optimizing two. The loss function to find W's and at the same time put constraint over this with this regularization. Okay? Actually, this is the actual name for this function if you are discussing or you are talking about this problem from the mathematical perspective. We are calling this cost function and this is the constraint. So we are always trying to judge or supervise the problem to make sure it will not go out of these boundaries. Okay? Now, what are the typical values for this regularization term? Actually, we have several, but the most common, well-known regularization functions is the L2 and L1. L2, sum all the W's and square them, and sum them. Sorry, square all the W's and sum them. One comes from the concept of modulus, okay? But if you use L1 here, in this problem, rather than using this, if I use what will happen here? It will equal sum of modulus W1. In this case, it will be 1 also. Here it will be sum of modulus W2 to equal what? Any difference between them? That's why you have to be careful. So only the L2 distinguish between them. L1 didn't do any distinguishing. Is this clear? So when you choose the regularization function, you have to be careful. It's not any function just to do the job. No. Some functions will work well in some problems, the other will not. So be careful when you choose your regularization function. Sometimes we combine both of them. As you can see, square plus modulus. This is good because we're adding two contributions to that one, right? But it has one drawback. What is this drawback? This beta. What is this beta? Parameter. Exactly. One extra hyperparameter, something that you should choose. So you're having now hyperparameter here and hyperparameter here. And increasing the number of hyperparameters is not a good thing, by the way. If you keep adding extra hyperparameter that should be chosen by the developer or the engineer, that reduce the quality of your technique. Okay? That's why we are not using that technique that much. But again, it's still used in some cases. Okay? Now, one of the problems that we always use to solve, or we solve using this regularization technique, is what we call overfitting and underfitting problem. What do you mean by overfitting and underfitting? Assume that we have those points. Now, assume those points we are collected from experiment. In the physics lab, in chemistry lab, whatever the experiment, in network analysis lab, whatever it is. And I asked you to expect or estimate the curve that join X and Y. What is the shape of that curve? Again, you don't know what is the relation between X and Y. And I give you those points. What's your expectation? Seriously?
An upside down parabola.
Okay. So if we consider it as a parabola, the parabola mostly comes symmetric somehow around some axes.
Sure.
Do you think there is any symmetry? Or you think it looks like this?
That's what I was thinking.
Okay, let's take this assumption. Now, if I give you newer points, and the newer points looks like this. Now, is your assumption correct?
Maybe, since it's still like between the new points.
The question is how we judge. We choose this curve because it passed through point 1, point 2, point 3, point 4. And we avoided this point, so we have only one error. Perfect. Now, for the newer model, how many points come next to this curve? Exactly next on the curve. Exactly. So that's what we call overfitting. So if the points I used to estimate, most of them came over my curve, and the newer points, none of them come on this curve. In this case, we are calling this problem overfitting problem. That's why we can't find a model by only some specific points. We have to divide any data I'm having into two categories. First category called training, which I will use to estimate the model. Another group I will call testing, which I will use to test my hypothesis. Okay? So if I give you any data, never, ever use all the data to build a model. Never. You have to divide them to at least two groups. The first one will be used to build the model. The second one will be used to test the hypothesis that you achieve. Okay? Back to this problem. What if I assume it's straight line like this? Is straight line better or the parabola curve is better? Let me change the straight line shape. Straight line or the parabola? Why?
Dividing them. Must be dividing.
Dividing what? How many points over this line? How many points under this line? Now look to the new points. How many new points over the line? How many points under the line? 2. So there is a balance now. Okay? Between the training and the testing, or the given data in the beginning and the newer data become a balance. Okay? It's what we call, so this is good model. And this one is overfitted. So if the curve give you good results during training, but with testing, it gives you bad results, this means your model is overfitted. Don't use it and don't think about it at all. So this is one of the worst scenarios you can achieve in the overfitting. A model like the blue, which is passed through all the points, completely perfect. But when it comes to the newer points that we achieve or we add last time, something like this, all of them out of the curve. Okay? But with this line, it become what? Almost balanced. Yes, it didn't pass through any of them directly, but it has a reasonable error between them. Okay? So that's what we want to achieve at the end of the day. You don't have to create a model that works perfectly with all the samples, but it should be balanced between your samples. Okay? So the error here almost equal the error here. The loss here almost equal the loss here. The accuracy here almost equal the accuracy here. Is it clear? Now, how this regularization help with that? Actually, the regularization, because it try to push the value of W to be smaller, it always try to go through the simple model. Yes. So you see, when I give high priority to the regularization, the model will be more simpler, like a line. If you give high priority to the data loss, the model will be overfitted, will be complicated. So as a rule, simpler model is more safer than the complex model. Okay? Any problems so far? Okay. So the regularization term considered to be the key point, the gate to protect our model from being overfitted and produce higher error. So, so far we learned the loss functions, even if it's support vector machine or hang loss, or the softmax function and the cross entropy. And we understand how the linear classifier is working. Anyone have any problem about this? Again, here we're still working with the linear classifier, which is very simple. F of W and X equal very straightforward and simple. Okay. Now, will this classifier work in all cases? Like this case as an example? Or this case, or this case? As we said before, no. Those linear classifiers are too simple to solve those problems. So I need another technique to handle those advanced problems. How we can do that? This said, I can solve this problem and overcome it by adding extra layers. What does this mean? Again, if I have the model look like this, then I'm having very simple one layer. Input, output, W. This said, and instead of having the input directly multiplied times W and produce the output, I will add extra layer. So I will have input, hidden layer, then out. In this case, I will have two W's. So first, I will apply X to W1, which will produce the hidden value. Then the output from here, I will apply to W2 to produce the final output score. And that's what we'll call multi-layer perceptron. In this case, I can keep adding even more layers. So I can have network look like this. You want to add layers? Add. No worries. 1, 2, 3, 4, 5, any number of layers you would like. Okay? And that's what we call deep neural network. So the word deep came from the concept of adding extra layers. So those extra layers should be able to achieve non-linearity, or sorry, better architecture to our network. Hold on. We have a problem here. What is this problem? Assume that we add one extra layer, like this. And we have them directly applied to each other. So the output here as H will equal W1 X. Then I will apply it to W2, so S will equal W2 H, which will equal W2 W1 X. That's the output, right? Now, this is W1, 2 times W1. Let's check the dimension. This input is a vector, so assume we are talking about image 3 by 32 by 32. In this case, I can convert this into a vector of 3072. So this of dimension 3072 by 1. Now, in this case, I have to assume the number of hidden nodes for this hidden layer. I will assume that I have 100 nodes. This is 100 nodes, means I'm receiving from here 100 signal. So this W1 should be 100 times 372. According to the rules of matrix multiplication, H must be 100 by 1. Now, this 100 by 1 will be multiplied times this. The output here is 10, so I have 10 nodes here. So this one is 10 by 1. So this W2 must be 10 by 100. Now, if we substitute H equal this will be 10 by 100, and this will be 100 by 3072, and this is 3072 by 1. I can do a matrix multiplication between those directly, right? So I can easily say that S1 equal W3, which is 10 by 372 by X. What did I do? It's the same exact linear classifier. So those extra layers doing absolutely nothing. They are useless. So I'm keep adding more layers for nothing. The problem is I can multiply those together. I need a barrier, separator, something that separates this term from this. So I can't multiply them. If I can do this, I can break this linearity and achieve a nonlinear system. That's why we said we will add something called activation function. It's a function that added in between the layers to achieve this nonlinearity. What is the shape of this activation function? Actually, you have several. One of them is this one, called rectified linear unit. This function is defined over two bases. So if you want to write it correctly, from x greater than 0, y equal x. If x less than or equal 0, equals 0. Defined over two bases. We can write a shortcut for this function, which is max. Max between 0 and z, giving z is the input x. Okay? Now, this function is nonlinear. Does it look nonlinear for you? What's the definition of linearity again? When I said this function is linear, what does this mean? And those are the two conditions of linearity. Are those two conditions applied to this function? If you look to this part, yes. If x positive, yes, it's linear. If x is positive, yes, it's linear. And all the conditions we are discussing here will apply to it. But for the negative part, is it linear? It's constant, it's fixed. So the nonlinearity here coming from the second part. We are judging the function as all. We are not divided into parts. We are judging it as a whole unit. Okay, so as all, the function is nonlinear. Now, if this is the only nonlinear function we can use, the answer is no. There are several. And by the way, we are finding new activations almost every year. The oldest two, and the one that used since 80s, maybe 70s, in this field, were the sigmoid and the hypertension. Hypertension. What is the sigmoid? Sigmoid, and always take the symbol sigma. It's 1 over 1 plus e power minus x. It looks like this, as you can see. At 0, exactly equal half. Exact. If you go deeper in the negative, it will equal 0. If you go deeper in the positive, it will equal 1. So it rectifies the signal to make sure that the output will never be bigger than 1. But if you have a negative input, the output will be what? I have negative x. Y will equal what? 0. So here is always 0. That's why we are using this function if the output of the node must be positive all the time. Because this node or this activation function don't produce negative output. Never. Always positive. What if your function or your output expected to have negative value? That's why we found the second, which is the hyperthane. Hyperthane is exactly similar to the sigmoid, but stretch it a little bit to the downward. So at 0 equals 0. If you are going positive, it will be positive with a maximum value of 1. If you are going negative, it will be negative with a minimum value of -1. So it saturates between -1 and 1. It will not give you any value more than that or less than that. Okay? Those two functions, as I was saying, used to be the two most famous activation functions until 2010 or 12 to be more accurate. They found this one, the RLU. The RLU, if you look, it's similar to the sigmoid. If the input is negative, the output is always 0. And the positive part is limitless. It doesn't have any limitation, like here. It can go to infinity without any problem. Okay? They found that the performance of the RLU overperformed the sigmoid. So this one is better in mostly all classification cases. Those, the 3 function only that we can use, the answer is no. Listen to this carefully. Continuous differentiable function can be used as an activation function. Any continuous differentiable function. Okay? Any function that you think about, continuous, if it's continuous and differentiable, can be activation. Any. Okay? So, based on that, they found those new ones, like the leaky RLU, which has straight from here, and here it's also linear, but with a different slope. Sometimes this one is trainable. So we call this alpha, and we can train it during the training process. It's not fixed. Sometimes. One decided to use this one, which is again 2 linear functions, but one positive and the other is negative. Another one is the ELU, which is linear from here, and from here it's exponential. So it has exponential part and saturation. Okay? Now, as we stated, this one considered to be a good starting for you if you are designing your own network. You can still start with this one. If this didn't work well, you can try to change it with any other one. But for most classification tasks, this one is okay. Now, if we apply the 2 layers network to our problem that we stated before. If you recall, when we apply one single linear classifier, one of the explanation or interpretation for this classifier was through templates or pattern, that those weights were nothing but patterns, templates to our classes. What if we apply 2 layers? How this interpretation will change. This said, if you recall, using this equation, this one is 3072 by 1. This is 100 from this 3072, meaning I'm having 100 patterns. Instead of having 10 patterns here, no, I'm having 100 patterns. How those 100 patterns would look like? Actually, this is an example of that. So as you can see, we have now more patterns. Some of them are repeatable. Like, you see this? See this? See this? This? This means that the pattern become redundant, which is not something good. So I'm wasting my computational power for what? For something to keep repeated again. But for some others, they are good. Like what? Like the horse. Remember when we discussed the horse? Actually here. When we discussed the horse, we said that the pattern for the horse or the template for the horse has 2 heads. Because some horses in the data set look to the right, some look to the left. When we have the deep version, this one, a complete template for the horse, look to the right, my right, of course. And this one, a complete pattern, look to the other side. So if we have more variation or more diversity in my pattern, I can easily find a template for them or a place for template for them here. Okay? Fortunately, some of them are uninterpretable, meaningless. Like this, like this, like this, like this, like this. Those are patterns for what? Do you see any of the classes, the 10 classes we discussed before, pointed here? So those become noise. Okay? This means what? This means I can reduce, actually, what the side of this? Those are 64 patterns. We still have about 26 more, or 36 more, okay? But at least for now, I can say that I can remove from here 1, 2, 3, 4, 5. So if I replace this with 95 nodes, my design will be good. Because those 5, they don't reflect a good pattern for my classes. Yes, the others reflecting or taking some patterns for some classes, but those are useless. So I can reduce this number to 95, maybe more if we look to the other 36 ones, okay? But again, I will not be able to achieve this without the nonlinearity. So the general shape will look like this. Multiply times W, having H, and here I must have non-linearity activation function of any type. Then multiply times W2, then another activation. W3, another activation. 4, another. Each H or each hidden layer must have activation function. Without activation, I can't have the nonlinearity. Okay? So as you can see, all of them have the nonlinearity. Without the nonlinearity, this, how many layers we have here? 7 layers? Almost. All this deep network exactly similar to one. Okay? Now, there is one rule we always have in the field of deep neural network, which is what? If you can't achieve what you want with 3-layer neural network, you will not be able to achieve it with a deeper one. Meaning, 3-layer neural network considered to be a shallow, universal approximator for any function or any task you want to achieve. Okay? So recently they found that this deeper network is useless. Having 3 layers is more than enough to do the task you want. And even when we go with the other type of neural networks, this one considered to be the only classifier or regression. So as we will see later, when we use the convolutional neural network or the recurrent neural network or the transformer architecture, any network that you think about, the last step will be this. And mostly 3 layers. Because if you can do what you want to do with 3 layers, no need to do it with the higher. Okay? So increasing the number of layers become useless. Okay? At some point, I remember by 2014 or 15, something like this, people keep adding layers. Like some people I saw having network which is 100 layers deep. Another person, what they did, you just increase this number. Rather than 100, you make it 1,000. But still 3 layers. So if you increase this number of hidden nodes, you can achieve this deeper architecture. Okay? So watch out from this problem. Okay, now how I can write code for that? Again, we will not use the traditional programming technique or the traditional Python programming technique to develop a deep neural system. We always try to use libraries for one single reason. If you write the code to develop a neural network by yourself, it will end up that the code will not be optimized. And the computational capability of your code will be low. So something that can run in 1 minute, it will run in 1 hour. Very simple. That's why we always use libraries. And I included a video on Canvas for how to use the PyTorch library. Okay? But if you will build the code by yourself from scratch, how this network will look like? This is a simple example of a simple 3-layer neural network that has simple input layer, output layer, also simple, and the number of hidden nodes is very small. So the input size is 1,000, the output size is 10, number of hidden nodes 100, and number of samples is 64. Okay, so this is 1,000. And then I have number of sample of 64. Here we are using NumPy library. Why NumPy? Because it handles the matrices. And what we are doing here, all the actions are matrix multiplication. So we need to handle this correctly. The number of samples we will use will be generated randomly. So I will generate 64 samples. Random samples follow normal distribution for inputs and for outputs. The value of W's, W1 or W2, the value of W's, W1 and W2 has to start randomly. So we need to guess it. Initial guess. This initial guess will be also generated using random generation. The initial value of W1 should be of dimension 100 by 1000. So it will be, the other one will be, okay? Then, for each n, so I will go through the whole entire samples together in one step. I will apply the input, dot product W1. Then I will apply the sigmoid activation function, 1 over 1 plus e power minus x. After that, I am generating the h value here. Then this h value will be multiplied times W2. This will produce the predicted score here. My task here now, is it a regression or a classification? Is it a classification task or a regression task? Who said classification? Okay, who agree with that? Okay. Who think it's a regression? Anyone? Who agree with that? How about the other? Is it classification or regression? The expected value of y, do we have it here specified to probability? No, it's randomly generated. So the task here is regression task. We want to have the expected output from the W equal those, from the Y here, equal those generated Y. It's a regression task. It's not a classification task. Okay? So once I have the Y predicted, I will use the mean square error function that we discussed, which equal 1 over n, summation over or n, y minus y bar, all squared. So y predicted minus y square and sum. The only thing that we remove from here is 1 over n, because 1 over n is what? A normalization term. This does not affect anything in the calculation. Just I'm normalizing them. Divide by constant. So this will be my loss value. Now, I want to adjust the value of W's here, W1 and W2. How I can do that? As we will see in a second, there is a technique we are calling gradient descent technique. So I am trying to find the derivative of L, this loss function, with respect to W, then subtract the value of W minus this derivative to generate newer value of the W. So this is a technique we are using to generate the derivative of the W's. We'll come back to this in a minute. Then we will substitute to the relation here with the value of alpha. This alpha equal 10 to the power minus 4. So the newer version will equal the older one minus alpha times the derivative. We'll keep doing this again and again and again, 10,000 times until we have a good version of the W that generated from this trained network. So this is a very simple network that can be used to build a simple 3-layer neural network. Okay? So now we learned about how the neural system is working. We learned about this multi-layer system and how we can build these architectures. Now the question is, what is the magic number of hidden layers we have here? If you recall, I said that this number is your selection. Is there a magic number that I can choose to this number of hidden nodes? And I told you we can choose any number of nodes as we want, right? Is there a magic rule for choosing this number of hidden nodes? The answer is no. But sometimes it's better to keep it low, because if you increase the number, as we said, we can achieve random patterns. These random patterns will achieve or will end up by having overfitted. Problem. So if you are working with 3 hidden nodes for this simple classification problem, as you can see, almost all the red samples included, but we have error here, we have error here, we have here, 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 here. This one, so and so. If you increase the number of hidden nodes to 6, as you can see, this one kicked outside, those one included inside. So the number of errors reduced. If you increase the number of nodes to 20, all of them sample correctly. But if I have now a new red sample, and the new red sample become here, or there, or there. In this case, here would still be error. Here, it will go with this region. So this is a bad case. This is not good, but also. Because this one is too simple. This is the intermediate, which is considered to be good. So having low number of nodes is not a good option, and having extremely large number of nodes is not a good option. Always try to be moderated, okay? Again, depend on the complexity of your problem. So as we stated here, after we start, for example, with 100 nodes, I can reduce the number of nodes after training and retrain the model again, okay? So we will learn how to choose this by experience. Again, as we saw last time, for the loss function, you can easily give high priority to parts of the loss over the other by selecting the value of lambda. So if you're having a bigger value of lambda, this means you're giving high priority to the regularization. So the model will be very simple. If you are giving smaller value of lambda, you are giving high priority to the data loss. So the model will be more complicated and overfitted. So again, you have to watch out for those parameters. So how many hyperparameters we have to choose right now? At least 2. Number of hidden nodes and the lambda. Assuming we are working on 3 layers. Okay? If you keep increasing the number of layers to look like this, the number of hyperparameters will increase rapidly. Because I will having hyperparameter for this layer, 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 which will make you get lost. Okay? Any questions so far? Again, I'm including here link for Andy Karpathy on his website, where he having simple classification example that show you the effect of the regularization. Keep changing it, you'll see exactly how the surface will, or the boundary between the sample will change. Okay, this example is built for convolutional neural network, built with JavaScript. Anyone know Andrea Karpathy? Okay, he's a chief engineer in Tesla. Any questions? Okay, let's take 10 minutes break, then we'll continue after the break.
How are you doing?
Okay, so what are you doing this for?
No.
So far, we learned about the network, fully connected layers, network architecture. We learned about the loss function. We learned about the regularization terms. We learned about the weights, the activation function, and nonlinearity. Now we want to learn about how exactly we can calculate this term. And why we need it. So to understand the problem, we'll start by a simple problem. Assume that we have a curve like this, okay? This curve is a simple parabola. Can we estimate the equation for this parabola? 5-point bonus if you tell me what is the equation. Okay, repeating the question again for you, Rich. Yeah, I'm giving 5-point bonus. If someone give me the equation for this parabola.
Which one, the top right, I'm hoping?
This is no problem.
Y is equal to 4x.
What is it?
Y is equal to 4x.
4x squared?
It's x squared, but it's like a transformation.
Obvious. So what's the equation?
Yeah.
So originally, if this here in the origin, we will have y equal x squared, right? This is original. But now we are shifting the vertex here to this place. This means we are shifting the x with 2 and we are shifting the y with 1, 2, 3, 4. So it should be y plus 4 equal x minus 2 squared, which is y equal okay. Now, if I told you that I want to minimize this function, how I can find the minimum point? This is high school.
By
What's that?
we keep x is equal to root of.
I give you function and they ask you to find the minimum, maximum, or the maximum of the function. What I do? This is high school, I'm saying.
Is this
The first derivative equals 0. This is where we have the minimum or the maximum. Right? So we will find the first derivative of this function. The first derivative is now if we add this equals 0, x will equal 2, which is this location. Then I can substitute with the equation again. I can get y. The y will equal, if you substitute here, the y will equal what? Minus 4. So the minimum point is 2 and negative 4. This is the traditional technique we are using when we studied calculus, the first calculus course, to find the extreme points. Okay, minimum or maximum. Now, can we apply this technique here to find the minimum point? Again, our goal here is to minimize function. So we have the loss function, and I'm trying to minimize it. So if we assume that our loss function look like this, for one reason or another, we're always trying to avoid this shape, but assume the loss function looks like this. If I apply this technique here, will I arrive to the same exact results? The answer is this technique, unfortunately, will be, if you apply it here, it will give me this, and this. All of those have the first derivative equals 0. All of them. Okay? So this technique is not working well with this one. One other problem. This one, I could formalize it, could find the equation for it and use this technique for it. Now, can you expect this function to formalize it? You give me the equation for this function, I'll give you A for the course. Anyone? So, formalizing this is not easy. Formalizing this was easy. So, to find the closed form for that and use the same exact technique is not a good strategy. Then how we can solve it? This said, I will use a simple technique. What is this technique? I will use numerical method. How the numerical method is working? Instead of working on the closed form for the function, I will work on initial guess. Let's say initial guess here. So I will assume that the initial value of x is this one. This is 2, 3, 4, 5. Okay. Now, for this 5, I will try to find the direction of the derivative here. I don't care about the derivative itself. I care about the direction of the derivative. Now, at this point, the direction of the derivative is positive or negative? Looks like this. It's going up because the next value is bigger than that. So we are going up, it's growing. That's why I will go against this direction. How about if you start from here? The direction from here is what? So if I go this direction, I work against the derivative as well. Okay? So I will go in this direction. And I will update the value according to this equation. So the newer value of x1 will equal x0 minus alpha, the derivative of f with respect to x at x1. This is to know the direction. I don't care about the value. I need only the direction. Okay? So I will work against this direction with a value of alpha. This alpha is a normalization vector. So I want to get small value within this direction. That's why this alpha is a small value, which always something like this, 0.001, within this range. So now let's apply this rule here. I said I will start with x0 equal 5. I need to find the derivative of the function at this 5. So if you substitute here with x equal 5, it will give you what? 5 minus 3 or minus 2 equal?
3.
Times 2 equal? So x1 will equal x0, which is 5, minus this small tiny alpha, 0.001, times 6. This will equal what? If you use your calculator, what does this number equal? Right? So I'm moving now in this direction. Let's repeat the same process again. So now I'll calculate x2, which will be 4.994 minus 0.001 times the derivative of the function at this one. So I calculate f dash at 4.994. Which equals what? I'll need the calculator. 4.994 minus 2 equal times 2, which equals 5.99 almost. It's 988. So 1 point times this. Plus 4.99. So equal. Again, I'm going closer to this point. Okay? Keep repeating this process 100 times, you will find that you will arrive to this point. This technique, actually, we are calling it gradient descent. So we are checking the direction of the gradient, which is the first derivative, and we are going against this direction with a specific parameter alpha. Now, if we apply this technique here, will it work? Well, what do you think? Let's see. If I take this point as a starting point, what is the direction of the derivative? Up. So if I use again the direction, it will go down. So I will keep going down, 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 down until here, and it will stop. Is this the point I'm looking for? Here it will stop here, which is the point I'm looking for. here it will stop here. Is this correct? Okay, now what if I take my point here? In this case, it will stop here. What if I take my point here? In this case, it will stop here. Are any of those are the correct point I need to stop at? No. But if I take my point here or there, it will stop where? Here, which is the point I'm looking for. Okay? So this technique is good, but has two problems. Problem number one, the selection of alpha. If you include this alpha to be 1 as an example, replace this value with 1. What will happen? 5 minus 6. The result will be what? Minus 1, which means I'm moving from here to here like this. Next sample, it will move like this. Next sample, it will move like this, like this, like this. So I'm not moving on the curve, no. I'll keep oscillating like this. So having large alpha can cause a disaster, which is called an oscillation. So I have to choose the value of alpha to be reasonable. Not small, not very small, and not very big. Of course, it must be less than 1. Okay? But increasing the value of alpha within some specific range will cause a disaster oscillation. So you will never achieve your results. This is the challenge number 1. Challenge number 2, as you see, selecting x0. The initial guess for x is a big deal. If you select the x0 in a place away from your minimum, your global minimum, it will end up by having local minimum. So you have to watch out for your initialization. So challenge number 2. So this technique is good, but you have to watch out for those two problems. Selection of alpha is a big deal, and selection of x0 is another big deal. And both of them are your responsibility. Remember, in the example that we solved right now, how did you choose the value of W? Initial value of W? How did we choose the initial value for W? Sorry?
It's a value.
Exactly. We pick them randomly that follow normal distribution, right? Is there any guarantee that those W will achieve the best loss function or zero loss? No. Okay, so the criteria for selecting the W's considered to be a big deal. Yes, if we consider them randomly, we will be, again, guessing. But if the loss function if it has more than 1 minimum, you may fall in a trap. Okay? So watch out for those two problems, because you will set those two parameters in the coding, even if you are using the library. If you are using PyTorch, if you are using TensorFlow, if you are using any of the available libraries, you have to set those two parameters yourself. No one will set them for you. Okay? Now, any problem or any question about this technique, the gradient descent? Now, my goal now is to find this derivative, because here I found the derivative of f with respect to x. So my goal now to find the derivative of L with respect to W, because this one that will give me the direction for the next iteration step. Now, how can I find this? This is the question that we need to answer. Assume that you are having this architecture as well. So you need to find the derivative of L with respect to W1. The derivative of L with respect to W2. The derivative of L with respect to W3. And so on. All of them. Because each one of them will require optimization. I need to include or use the gradient descent with this, with this, with this, with this, with all of them. Can we do this from this equation? This is the equation of that's the final output, right? Can I use this equation to find the derivative with respect to W1 or W2 or W3, W4? Can I? This is the trick. And to solve this problem, we are using something called backpropagation. So my goal now is to find this derivative of L with respect to all the W's, all the parameters I'm optimizing in the algorithm. So we will start from the definition of the slope or the derivative. This is the definition of the derivative. If you recall from, again, calculus. So if I can find the derivative of L with respect to the W, congratulations. You solved the problem. We can do this in two ways. First technique, analytical, meaning I'll start from the equation of the loss function. Again, this is the data loss. And this is called what? What is this other term? Regularization term. Okay, so the loss included both of them. Not only this, not only this. Now, if I want to find the derivative of L with respect to HW from those, I can start to do the job analytically. Okay. Here is the analytical derivation. Good luck. Start with this function for one loss function value, find the derivative, then make a substitute in the bigger one, then find the derivative with respect to W, which will include those terms, and so on, and so on, and so on, and so on. Which is okay, you can do that if you would like, okay? But what after you change this, you found that, what type of loss we are using here? What's the name of this loss? Actually, the name is here. Hang loss, the SPM. What if you found that this loss doesn't give you a good result? And you decide to change it to cross entropy? What you'll do? Remove those equations and redo it with the cross entropy, right? Good luck. The equations will be much bigger than that, especially if the network is deepened, okay? What if the cross entropy didn't give you a good result? You want to move to mean square error. Keep repeating the same thing again. Does this make sense? Every time I choose a loss function, I have to keep repeating all the process again, back and forth. Doesn't make any sense. That's why we said we will use a concept of chain rule. Well, how this concept will work? What is the chain that we will work with? They said I will start to build something called computational graph. To the computational graph. It's a simple nodes that work together to produce the next step. So here as an example, I'm having X and W, one simple linear node will be multiplied together to produce the score. This score will be applied to the hang loss and will be compared the ground truth or the regularization term to produce your final loss value. Now, I want to find the derivative of L with respect to this W. This said, simply, I can easily use the back propagation or chain rule to find this derivative by finding the derivative between this and this, then between this and this, then between this and this, and so on. which using the concept so I can calculate this by itself, I can calculate this by itself, then I can multiply this times this to produce the loss, the derivative of the loss with respect to the double. Let's have a small example. So assume that I have this node. I have x here, y here, both of them added together will produce q, then q multiplied times z will produce f. So the equation for that looks like this. Now, I want to start to find the value of f, the derivative of f, with respect to x, and the derivative of f with respect to y, and the derivative of f with respect to z. Using the technique we just explained. How we can do that? They said, first, we are working numerically, meaning I need some input value here. So I will assume that we are doing this at x equal to 5, y5, z equal -4. So -2, 5, -4. First, I will go forward, meaning I calculate the value of q and f. First, the value of q will equal 3. The value of f will equal what? We are going forward. Now it's time to go backward. So I'll start first by finding the derivative of f with respect to itself. The derivative of f with respect to itself will equal what? Derivative of a variable with respect to itself equal what? Simple. I'll find the derivative of f with respect to q. If you look to the equation, f equal q times z. Now, if I'm calculating, this will equal what? This is a partial derivative, not a full derivative, because all those are variables. Okay? So when I take the derivative with respect to 1, I have to make all the others are constants. Now, what is the value of q that I'm having here? So this is equal to. Did I use any equation right now? Did I find the complication of the function? I used the numerical value that I applied for the input to calculate the derivative back in the for the output with respect to the inputs. Okay? Now I found this path. So this is 1. Then the derivative with respect to z will equal 3 according to the calculation we just did. Okay? How about the derivative of f with respect to q? Again, from here, the derivative of f with respect to q will equal z. The value of z is what? So this will be -4. Again. Okay? Now, I want to find the derivative of q with respect to x. U equal x plus y. So the derivative of q with respect to x equal what?
5.
Equal?
3.
Oh,
The second one is constant with respect to x. So the derivative is 1. Now, I can say that the derivative of f with respect to x equal the derivative of f with respect to q times the derivative of q with respect to x. Now I got this, and I got this before, which is -4. So the derivative of f with respect to x will equal -4. Same for the y. So if you are finding the derivative of y, again, to equal the derivative of q with respect to y times the derivative of f with respect to q. This is, we already calculated -4, and this also will be 1. So it will be 1 times -4 equal -4. Now, on this chart, we found the forward values and the backward values. Congratulations. Now, you can update any of those parameters. You have the derivative of f with respect to x, derivative of f with respect to y, derivative of f with respect to z. I can update the value or no? Yes. Okay. This technique, what we call the back propagation technique. So I'm calculating the derivative of the loss with respect to the parameters step by step to the back. Okay. Now, can we generalize it? Yes. So if we have any node, the derivative of the output with respect to the inputs can be calculated in 3 steps. First, I'll calculate the upstream gradient, which means the gradient of the loss with respect to this output, times local gradient, which is the derivative of this output with respect to each one of the inputs. Then multiply this times this will give you the final loss, which we call downstream gradient. So I calculate upstream gradient, local gradient, multiply those together to calculate the downstream gradient. Any node can be calculated this way. Okay? Down, local, sorry, up, local, down. After we calculate this, can go even further. So go to the previous node, go to the previous node. So if you have 100 layers, no matter, you can do it. So this is another example. I have W0, X0, W1, X1, and W2. And I want to find the derivative of final F with respect to those 5 parameters. Again, we are working numerical, means I have to have a specific numerical value and first go with the forward path, then I will calculate the backward path. So for this example, I'm having W0 equals 2, -1, -3, -2, -3. So if you calculate the forward path, those are the calculated value. You can double check them if you like. Now we want to go backward path. Again, we always start from here. The derivative of f with respect to itself, which is always what? Now, this is the upstream. I have to calculate the local gradient for this one. What is the derivative? Of 1 over x. Any calculus?
-1 by x square. -1 by x square.
Okay. So 1 times -1 over x squared will give you the value here. What is the x that we apply? X is working numerical. So we have this x that we apply. So we calculate this value, multiply times 1, will give you this gradient. Now, this is the upper stream for the next one. This is the local. So this will be f equal x plus 1. What's f dash? So it will be 1 multiplied times this one will produce this. As you can see, 1. Now I'm having exponential. What is the derivative of the exponential? Same function. So I will substitute with minus 1, it will give you 1 over e. Multiply times this one, it will give you minus 0.2. Again, this are the upper stream for the next one. What is the gradient of this? So minus 1 times this will give you the gradient here, 0.2. Here we have fork. So this function is x plus y. So I will have 2 branches. The derivative from this side will be y, and the derivative from this side will be x. So here, I'll take the derivative over this side. So it will be minus 3 times 0.2. And from this will be 4 times 0.2. So 4 times 0.2 will equal, sorry, did I calculate it? Oh. So f dash with respect to x will equal 1. F dash with respect to y will equal 1. So 1 times this 0.2, 1 times this 0.2. Again, another addition unit. This will be 1. So 1 times this 0.2, 1 times this 0.2. Again. Here I have a multiplication point. xy. The derivative in this case with respect to x, the derivative with respect to y will equal x. So the derivative here will be minus 1 times 0.2. The derivative here will be 2 times 0.2. So it should be 0.4. Here the same thing. The derivative here is minus 3 times 0.2, and here it's minus 2 times 0.2. So this way, we found the derivative over all the leaves of the tree. Even if it's bigger than that, keep going. Then I can now update W0, X0, W1, X, any variable that I need to update, I can update it. Any problem? Any questions? Now, if you look to this part is nothing but the sigmoid activation function. Can we replace this with a node, one node of the sigmoid, and we can apply the upper stream here, downstream here, and find the local stream for the sigmoid? He said, yes. Can we find the derivative of the sigmoid? Here is the derivative of the sigmoid. The derivative of the sigmoid equal 1 minus the sigmoid times the sigmoid. And here is the proof. Very straightforward. So if you apply this technique, you will substitute with the value of x here, which is 1. Then find the derivative. 1 times this derivative, it will give you the 0.2. Try it and it will be valid. Okay? So If you apply it, you can calculate it directly. 1 times this derivative, this is the local, it will give you a 0.2, which is the same exactly the downstream. That's why when we start talking about the activation function, I gave you 2 conditions. What are the 2 conditions? It has to be continuous and differentiable. That's why. 2 can go with the forward and reverse and back propagated path. So if the activation function is not differentiable, it will break this rule. All the functions that we introduced are differentiable. Starting from the sigmoid, the hypertense, the RLU, the leaky RLU, the max out, the LU, all of them are differentiable. So we found that the derivative of the sigmoid. Anyone know what the derivative of the hypertense? Nothing? No trigonometry? Hypersec, sec squared, sec squared. That's how we call it. Okay, which can be related also to the hypertan using the trigonometric relations. So if you want to look to the value, that's how it is. 1 minus hypertan squared. Okay. The RLU, here is the derivative for it. The leaky RLU, here is the derivative for it. Okay. All of them we can find the derivative for them. Okay. Think about any function, we can find the derivative. That's why any function, and when I say any, I mean any, that's continuous and differentiable can be an activation function. You know it or you don't know it. Okay? Any problems so far? Okay. Now, what is the derivative of the loss function itself? We learned how many loss functions so far? 3. Hang loss, cross entropy, and mean square error. Let's start with the mean square error. Now, what is the differential of this one? Again, with respect to yi par. Those are some terms. So 1 over n is constant, I will not touch it. The summation will stay also, I will not touch it. Okay? Now, what is the derivative of this bracket? 2 yi minus yi par, and I remove the square. Time the derivative of the y par r, depend on if it starts here or there. So if we start it from here, it will be positive. Interesting. If we make it like this, the derivative will be positive. If we make it like this, switch them, the derivative will be negative. Okay? But in all cases, it will not make any difference. Okay? So this is the mean square error. The second one is the Hang loss. This is the derivative of the Henn loss, which is nothing but a maximum function, okay? And the maximum function can be divided into two categories, two bases, and we differentiate each base separate from the other, okay? It's very straightforward. How about the cross entropy, which have this function? What is the derivative of it? Any suggestion? What is the derivative of the log? This is logarithm, right? What is the derivative of the logarithm?
One by P.
I have logarithm. Or len, to be more accurate. This is len. Logarithm base e of x. In this case, the derivative is 1 over x. Okay? Now, I have another parameter here, which is what? The softmax. Because this is the probability. So after substituting with the log, I have to find the derivative of the softmax. What is the derivative of the softmax? Is the derivative of the softmax. Okay. If you do all the calculations for the cross entropy loss function, you will find that the derivative of L with respect to the expected value equal that's it. The difference between the expected and the ground truth, which is very close to the mean square. Okay? Which is really weird a little bit, but it's proven. We can easily prove that. And the proof can be 2 pages, so long a little bit, but we can easily prove that the derivative of the cross entropy function is the expected value minus the ground truth. Okay? So now we have the derivative of all loss functions and the derivative of all well-known activation functions. If I can add a new activation function, you should be able to find the derivative for it. Okay? Anyone have a problem with the derivatives? I think you should refresh your calculus skills a little bit. Okay? Now, to make things easy, we will start to go with pattern. Nodes will look like a pattern. So if we have addition node, in this case, the derivative will be easily distributed over the all branches, which is correct because this is the downstream and the local here, or f will equal x plus y. So the derivative with respect to 1, when this is 1, the derivative with respect to this is 1. So 1 times this equal this, 1 times this equal this. So addition node just distribute the gradient. Forking node, or we are calling it copy gate, we are adding the derivative. So if the same output distributed over 2 branches, if the derivative of these branches is 4, derivative for this branch is 2, the derivative here will be the sum of those. Again, come from the concept of chain rule. If I have the derivative of L with respect to H, let's say H, this is equal. The derivative of L with respect to, this is H1, then H2 times the derivative of H2 times H1 plus the derivative of L. So this is the first component, and this is the second component. Finally, this is the derivative of L with respect to H1, and this is the derivative of L with respect to H1. So I have to add them together to produce the final derivative of L with respect to H1. Okay? This is if I have forking. If I have multiplication node, multiplication is very easy. The derivative here, this time this. The derivative here, this time this. The derivative times the other input. It will give you the derivative of the branch. Very straightforward. Finally, if I have the max, as we said, the max gate or the max operation has two bases. Okay? While you are going forward, we are taking the maximum between them. While you are going backward, the one that we took at the maximum will get all the derivative. The other one will take nothing. Okay? So based on that, we can easily build the gradient, forward path, and backward path for any network that we need, which is exactly what we did, if you recall, for this application. You see here, that's what we did. We start by the forward, then we did the backward step by step until we arrive to the derivative of L with respect to W2, the derivative of L with respect to W1, then we apply the gradient descent. Okay? So this is the main concept or the main idea of the backpropagation. This concept applies to any type of network, starting from the linear one node or one layer, this one, ending by GPT-4. The concept applies to all of them, no change. Okay? So if you don't understand it, you will face many problems later with our work. So if you have any problem, please let me know right now. Okay. Okay. Any questions so far? Okay. Now, again, what we are discussing right now is reasonable and good. But the problem is when we apply input data, are we applying it sample by sample, image by image? If you look to the example that I just showed you, we generated 64 samples, and we are using all of them at the same moment, right? So working with the backpropagation need to be adjusted a little bit to handle the nature of my data that I'm applying bulk, chunks of data, rather than one by one. How can I do that? I need to adjust whatever we covered so far for the simple derivative technique into a multi-dimensional derivative technique. In this case, the derivative will call a Jacobian. Okay? So if I'm having vector of x and vector of y, which will generate vector of z. In this case, I'll calculate the derivative of the upstream, and I will calculate the Jacobian local matrix, then multiply this times this to produce the downstream. So this local part will be a matrix, and it will be a Jacobian matrix. Not only one value like what we did so far. No, it will be more advanced one. So in this case, if I'm applying an input to the max function, in this case, the output will be like this. In this case, if I calculated the derivative, it will look like this, the Jacobian matrix. Then I will multiply this times the upstream to generate the downstream derivative. So here I'm not working with one value here or there or there. No, I'm calculating the derivative for all this vectors. Okay? So this way I can reduce the calculation time and can make the computation much more efficient. Again, there are some tricks we always use to handle this, but again, we are not going with the programming technique right now. So this is also another technique or another way to look to the backpropagation problem as the chain rule, as we stated in the beginning. So I will start by the loss function, and to calculate the derivative with respect to anyone here, I'm applying chain rule backwards. Okay, so this is another way to look to this technique. Any questions so far? Now the question is, do we need to do all those calculations manually for every network we will use? The answer is no. All modern libraries has an auto gradient capabilities that you can activate and will calculate the gradient for you. Okay? But you need to learn how to do the gradient in case you need to build your own, which is occur a lot right now. So if you can't build your custom node here, you are in a big trouble. You need to learn how to build your custom function here and build its own gradients. Okay? Because that's how we build the networks nowadays. Yes, there is an automatic calculations, but if the gradient of the function that we have here is not available for the computer to find the gradient for it, in this case, you have to build the gradient by yourself. And also this is included in the video I'm adding on Canvas. Okay? Any questions? Any problems so far? Okay. Okay. Now we understand what is the backpropagation, and we understand the concept of gradient descent. Now, not the gradient descent always good for us to use or to do? The answer is not really. Why? As we stated, we have to choose the initial value by ourselves. We have to choose the learning rate ourselves. And if you have limited computational capability or limited time, you have to choose the number of steps also yourself. Usually we are calling this number of steps epochs. Okay? Now the question is, can we improve the quality of this technique? He said yes. How? Instead of working on the whole entire samples. Again, this n should be the number of training samples. So I should find the sum of all the loss or all the errors for all input samples. And based on that, I'll calculate the loss function and find the derivative based on this all sum. This said, okay, if we assume that those samples are a population and we are doing tests on those populations, should we get the vote of all the people in our population? Like, for example, you have a new medicine, right? And you want to test it. Should you apply this medication to all people in Connecticut to test its validation? If that's how we are doing it, then how we are doing it? If you want to test a new medication, what should you do?
Test it in food.
Exactly. So I have to select some volunteers to test the medication over them. I will sample from them, and the samples should be randomly and unbiased selected. Means it should represent my population, one way or another. Okay? This said, I will do the same exact thing here. Instead of working on the whole entire population to find the loss, then calculate the gradient based on this total loss, I will sample. I will take small samples from that, and I will call this mini batch. Okay? So those all my samples, I will take 32 samples from that. Calculate the loss for the 32, then find the derivative. Then calculate another 32 samples. Do the same thing. Another 32, and do the same thing. This technique will be better from the computational perspective. Why? Because instead of doing the training, assume that we are working on GPT model as an example. Okay? Do you know how many curves or words used to train the ChatGPT? Anyone know? Billion, trillion. Lots and lots of that. Okay? So if you are using the gradient descent with the original form, you have to find the derivative after you apply all those training samples, which doesn't make any sense. That's why I will reduce the time a little bit by having the mini batch, which can be 32, 64, 128, something reasonable for the calculations. Okay? And after that, I will calculate the derivative based on this smaller sample rather than of overall the training data. And I will call this technique stochastic gradient descent. Because the derivative I find right now is not derivative over all the errors, no, over sample errors. That's why it's a stochastic gradient descent. The problem here that I added one extra parameter here. The batch size. If I choose a batch size of 32, will this give you the same performance of working on 1 trillion sample? What if I increase it to 128? Is it better or 32? Is it better or 64? Is it better or 1000? So I have something else to take into consideration in my calculations, which is one extra hyperparameter, because you have to choose this yourself. Another extra technique has been added, which is sampling method. How you will select those samples, how you guarantee that the samples are not biased. Okay, will you sample with replacement or sample without replacement? So the sampling technique become a problem by the one extra problem for you. So this technique faster than the original gradient descent, but adding extra responsibility over you as the developer or the engineer. So in this case, if you want to compare the performance of the gradient descent compared to stochastic gradient descent, so I want to show you a small video. This is the stochastic gradient descent. See, it's not going straight. If you look to the original, this is the gradient descent. You see, smooth going to the minimum. Stochastic is not smooth, it's struggle. But it has one advantage. It will go directly to the minimum. If you look to the gradient descent, it's moving like this. Doing here, fast, fast, fast. When it approaches the minimum, again, this is the minimum. So this dark red is your minimum, okay? So it will go like this, fast, 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 fast. Then it will slow down here. So it can go with these steps, 1, 2 steps. Then from here to here, can take million iteration just to go to this part, okay? The stochastic is going more towards here. But again, is it stable? No. Depending on what? Depending on your sample, number of sample in the mini batch, number of samples in the mini batch and your sampling. Okay? Is there another technique that overcome the problem of the gradient descent and the stochastic gradient descent? Yes. Okay? And that's what we'll cover next week. But just to let you know, stochastic gradient descent is one of the best technique we can use to train large models. Okay, as you will see later, there are some other more techniques like Adam and other model, Adam W and all those. Those are not working well if the number of the parameters in your model increase rapidly. Working with the stochastic gradient technique become much better, especially if we add some adjustment to it, which we call stochastic gradient descent with momentum. Okay, we'll come to this point later next week. Any questions? Again, I'm spending more time with this part because those are the basics. After that, the change will be in the architecture only. But the concept that we are using now will be applied to any architecture. Okay? Any questions?